Okay, so I want to do one more example here of where we have a system in equilibrium. So we've got a system in equilibrium, and we're given it the weight here, W2 hanging down is 200 newtons. We want to find the tension T1, T2, T3, and we're going to find the weight of the other object here. So to do this, we're going to do, just like we've done in the other examples, I'm going to start off by making, in this case, I'm actually going to make two free body diagrams, and then it's just going to be a matter of sort of relating everything together. Shouldn't be too bad, I hope. So let me call this the point A, and I'll label this little point as point B. So there's our point A. So we've got the weight acting, W1. We have our tension here, T3. Then we have our other tension here, T2. And then we've got our other diagram here. So here's the point B. We've got our tension T1. Again, we have the tension T2. And we have the weight W2. But we're given, again, the weight, and we're told that the weight is 200 newtons. Okay, so we're also given this angle, that is 37 degrees. And now what we're going to do, again, just like in the other examples, we're just going to break things down into horizontal and vertical components. And we're just going to use the fact that the net force will be 0 to create some equations. So again, just like before, to get this vertical component, we could simply use sine of theta. We would get that the vertical component has the vertical component is T1 times sine of 37 degrees. Our horizontal component will be T1 times cosine of 37 degrees. But we can use the fact here, if we sum up the forces acting vertically, that's going to have to equal 0. So that tells us that T1 times sine of 37 degrees minus the weight, which is 200 newtons, that's going to have to equal exactly 0. So that's going to allow us to solve for T1. We can add the 200 newtons over. We can divide by sine of 37 degrees, and that's going to give us the tension T1. So I've got my handy-dandy calculator here, so let's see, I'm going to round stuff off. So I'm getting that T1 is going to be 200 newtons divided by, let's see, sine of 37 degrees. If I round that to 3 decimal places, I'm getting 0.602. So let's see, 200 divided by 0.602. I'm getting that to be 332.226 newtons, again, after rounding. Okay, so now we know the tension T1. So still working with my diagram here on the right, we also know that if we look at the forces acting horizontally, those have to equal 0 as well. So that would tell us that T1 times cosine of 37 degrees minus T2, that's going to have to equal 0. So again, I'm just looking at the force, kind of pulling it to the right and pulling it to the left. That net force is going to have to be 0. Again, well, now we know T1, so let me substitute in that value. We could also add T2 over to the right, and now we'll know the tension T2. So let's see, T1, we've got 332.226. Again, let me simplify. Cosine of 37 degrees. So cosine of 37 degrees, I'm getting that to be 0.799 after rounding. So let's see, 0.799. Try that one more time. 799 multiplied by 332.226. And again, I'm going to round off here, so I'm getting this to be 265.449 newtons after rounding. So now we know the value of T2. All right, so Now I can turn my attention to our diagram here on the left. So again, we said the angle there was 53 degrees, so let me fill that in. Now I'm just going to do the exact same thing that we did on the right, break this down into vertical and horizontal components. So here we would get that the vertical component is going to be T3 times sine of 53 degrees, and the horizontal component is simply going to be T3 times cosine of 53 degrees. Well, now I can use the fact that we have T2. So if I look at my diagram here on the left again, we know that the sum of the forces acting horizontally will have to be 0 since it's an equilibrium. So that would tell us that T2 minus T3 times cosine of 53 degrees, that's going to have to equal 0. So again, in this case, we know T2, so let's go ahead and fill in that value. So that's going to be, let's see, 265.449. So that's our T2. And let's see here. We could add T3 times cosine of 53 degrees over to the right. So we would have T3 times cosine of 53 degrees. But I'm just going to go ahead and divide both sides by cosine of 53 degrees. And now, again, let's just simplify. So we have 265.449 cosine of 53 degrees. I guess really we've got that value already. Because, right, cosine of 53 degrees is actually going to be the same thing as sine of 37 degrees. So if we round, again, that's 0.602. Again, this is in newtons. So let me simplify. 265.449 divided by 0.602. Let's see. So I'm getting 440.945 newtons after rounding. So there's our T3. The only thing left now is to find the weight, W1. But again, we can use the fact now that if we sum up the vertical forces, that's going to be 0. So if we take T3 times sine of 53 degrees, so there's our vertical component, minus the weight, W1, that's going to equal 0. So alright, we're almost there now. So let's see. We can add W1 over. T3 again is right down here. We had 440.945 newtons. Sine of 53 degrees, that's going to be the same thing as cosine of 37 degrees, and we rounded that and said it was 0.799. So now all we have to do is this last bit of arithmetic, and we've got every value that we wanted. So let's see, 440.945 multiplied by 0.799. I'm getting this to be 352.315 newtons. All right, so there we are. We've got everything related. So this seems to be, the gist on these problems, again, is just setting up these free body diagrams. And, in certain cases, if you have lots of weights or sort of lots of points that are in equilibrium and you're trying to find all these different tensions, you may have to set up quite a few different little free body diagrams. But then it's just, take the diagram where you have some extra information, use that to figure stuff out, and then you can simply start relating that to other pieces in the system.